Alright, welcome back to the second part of strength of material, fixed cylinder. In the previous video we spoke about the single cylinder and we explained everything, the analysis of different stresses, and how are we going to accomplish each of them, their variations and their differences. On this one, we're coming to explain about the compounded cylinders, meaning the compounded cylinders consist of two cylinders which shrunk together, e.g. hub shrunk into a hollow or solid. So usually we feed shafts inside the hubs, so that's where we're going to have the compounded cylinders, meaning we have 2 or 3 cylinders and as one package. So we're coming here to understand about what is going on there. In this chapter, or in this unit or part of the module, we're going to separate our unit into two. We're going to have a shrinkage and the internal pressure, meaning first we are at compounded cylinders. We are here now. We are at compounded cylinders, and we're going to split our compounded cylinders into two. We're going to have shrinkage and we're going to have internal pressure. So we basically splitting our compound cylinders into two, meaning when we talk about shrinkage, it's a way of when two cylinders are shrunk together, we know that the inner diameter of the outer cylinders will not be the same as the outer diameter of the inner cylinders before they shrunk together. But once done, the diameter will be the same, because one has to compress, the other one has to stretch. So that's what is happening with shrinkage. We spoke about, let me give a simple drawing here before I can go further. We spoke about a single cylinder being something like this, where we say that okay, we're gonna have the internal diameter and we're gonna have the external diameter. So now I need us to name this X. It means we're now introducing another cylinder on top. It means it's already shrunk. Then we're gonna name this one Y. So we now have two cylinders, 1 and 2. So if you check, we're going to have 3 diameters. We're gonna have the internal diameter, we're gonna have the intermediate diameter, and we're gonna have what, the outside or the external diameter of the outer. So we have what, the inside and the outer. Remember, when we were having a single cylinder, I made a simple drawing where I said we're gonna have the 3 diameters, where we're gonna have the, here I said here we're gonna have the what did I say? We're gonna have the bigger diameter, we're gonna have the thickness if it's wanted, like the one on the thickness if it's wanted, and we're gonna have the internal diameter. So on this case, I need us to consider something very important. We're going to have this diameter here, which we're gonna name it D, and we're gonna have this diameter here, which we're gonna name it DI. DI meaning is the intermediate diameter, and we're gonna have this diameter here, which we're gonna use D. Or let's use this as a DC, because at first we said that other one is there, it's DI. So let's say this is DC, right? So it means our bigger diameter is going to be here, then this is going to be our DC, and this is going to be our D. So it means this is the outside, this is the outside, this is the inner, like at the contact, this is the contact point where the two are making a contact and meaning this is the internal. This is the internal, meaning this is the internal. So this is our outside, this is our contact. That's why I said let's use C. It means it's a contact diameter, and this is our D, the small one inside. So we now going to change our drawings. Remember, on the single cylinder I said we're going to use something like this. On the single cylinder, remember I said this is our D and this is our internal one. Then I said here is going to be our 0, and our sigma R QR, sigma R is gonna be here, and our sigma hoop stress is gonna be like this. Remember, and I say here we're going to have what? PI, internal pressure. So on this case, we're going to avoid internal pressure on the shrinkage. We're going to avoid the internal pressure on the shrinkage. So on the shrinkage, on this case, we're not gonna have the internal pressure, but we're gonna have an internal pressure here when we're gonna talk about it. So now let's focus here. So we now know that on a shrinkage, we're going to neglect the internal pressure. So how are we going to draw our new sketch? If we had to draw a new sketch, then our new sketch, I need you to know this. Keep this in your mind and heart, so that you will be able to draw it when we are answering questions. It means when you're going to draw this, the same structure is going to apply only here. Remember, from outside, which is here, to the contact, it's the outer cylinder, and from the contact to the internal, which is from here to here, is for the inner cylinder, right? Good. So from here, it means we're gonna have what? Outer. We're gonna have an outer cylinder, and here we're gonna have what? An inner cylinder. One can come and name this Y or name this X. It's still one and the same thing, and it means this diagram for the single cylinder will come to apply for the outside one, meaning we're still gonna have the same shape here from point 0 to here to the contact point. Do you see? To the contact point. Then we're still gonna name this what? Sigma R. You see it? And we say, okay, it's still gonna come and go from the outside to the contact, and we're still gonna name it a sigma hoop. You see it? Then I'm telling you this. If they say calculate the hoop stress on the outer, you have to come here between these two, and either on this diameter or on this diameter, the question will state calculate the hoop stress on the outside diameter. Then you're gonna come and calculate it here. Then this applies like that. So here it is no longer a internal pressure. I said we not going to talk about the internal pressure. It means this, we have to go inside and identify this point. When we go inside, our statement now, our graph now is going to change, meaning from here it has to go back. It has to go back here, and we know this, our sigma R, or stress of radial at the inner, is gonna be like this. But our hoop stress at the inner, it's not negative anymore. Remember, here on the single it was negative. It means now it will take this kind of a shape on top. It means it's now gonna take this kind of a shape on top. It means our hoop stress now here, it's no longer 0. So let us make important notes about this. Let us make some important notes so we know that a hoop stress in an outer cylinder will be tensile. Hoop stress on the outer cylinder will be tensile. It means Q hoop, a sigma hoop on outer will be tensile. Will be tensile, and it's gonna be negative. It's our Q hoop on outer, is this one on outer. It's going to be what? Tensile, and it's gonna be negative. Then it means our sigma R on outer will be positive, will be compressive, right? And it's gonna be positive. You get it? Then we are still on outer. Then now we go to the inner. Let's go to the inner. This is outer cylinder or cylinder Y. Now we go to the inner. Let us look at the Q hoop. So we know on the Q hoop, the Q hoop, sigma hoop and sigma R, which is hoop and radial, will both be compressive. This is what we know from now on. They will both be compressive, meaning if they are compressive, they are both positive on a shrinkage basis. So they are both what? Positive. It means a hoop and radial stress in the inner on X, they will both be positive. And we know one thing, that now we are given a new statement here. They told us that a radial stress and on the inner and the radial stress on the outer will be equal at the contact place. Did you hear what I said? A radial stress on the inner and the radial stress on the outer will be equal at the contact diameter. It means the radial stress of this of Y and the radial stress of X, they will be the same on the contact area. That's why they are at the same point here. Do you see it? And we know as well that the radial stress at the outer diameter is 0, and the radial stress of what at the inner diameter is 0. So here at the inner and at the outer, our radial stress is 0 on a shrinkage. This is what we know from this graph. So this is such an important information that you need to absorb. So we need to know, we spoke that the maximum it's where? It's on the maximum it's always on the inside, and the minimum is always on the outside. Remember, that's what I told you from the single cylinders. So if we are told that the Q hoop at the minimum, let's say they say we must find Q hoop at the minimum. So this statement, it is true for the compound cylinders, that any diameter of the outer cylinder at any diameter is going to be like this. Look, I'm writing this equation for you. I'm writing this equation: sigma R plus sigma H equals to contact place, right? And equals to 2A. It's even equals to Q sigma H minimum. You saw that? And we make a conclusion again, and we say sigma R plus sigma H equals to C equals to 2A and equals to what? Sigma H maximum. What am I actually trying to say? It means if I am saying this, I'm actually trying to say that hoop stress at minimum, right, is equals to hoop stress at maximum according to shrinkage. From my statement, this is what I'm trying to say. The hoop stress at what? Minimum equals to the hoop stress at the maximum according to this statement. But this thing, it's only applying, it is true for the compound cylinders, that at any diameter of the outer, remember, at any diameter of the outer. For now, don't mind this statement. I'm sorry for it. Don't mind this statement. Let me explain this one first. Listen to this. This one, it's only on the outer cylinder. It applies on the outer cylinder. And this one, it applies on the inner cylinder. You hear me? It means at any given diameter, of the outer, this statement is true. It means QR and Q hoop, they are the same for what? Q hoop minimum. and this one QR and QH, they are the same for what? QH maximum, but on the inner. That statement is clear, right? And immediately I want to explain about the internal pressure, and so that I can combine them and I can now show you the relationship between the two. When you talk about the internal pressure, we're talking about the pressure that is happening throughout. At first, the internal pressure on a single cylinder was on the inside. It was happening on the inside of the cylinder. Same things applies here. It means for the internal pressure, we're still going to use the same graph method, but this time it's going to be a little bit different. Meaning here we're going to have the outside diameter. Here we're going to have the internal or contact diameter. Here we're going to have the internal diameter. It is the diameter that is inside. So now we say that the internal pressure will act on the internal pressure, on the internal diameter. Same thing that was applying on the single cylinder. So when we see internal pressure, we always treat it as a single cylinder. That is the statement. We always treat it like what? Single cylinder. So we actually seeing DC as a you remember on the single cylinder we were having something like this, right? And this is the internal diameter, which is D1, and this is the outside diameter, which is D. So what is DC on a single cylinder? It means it's gonna be the diameter, the middle on the thickness. You see it is the one that is here. So DC is, we now gonna treat it as if like it's a single cylinder like this, meaning our drawing is not gonna change. It's gonna go straight like this from 0 to there. Then it means this is gonna be for on point positive and negative. This is gonna be our sigma R and our sigma hoop. Then when it goes up, it means to this point is going to be P1. Our pressure internal is still acting on the inside of the cylinder. So this is not gonna change. It's gonna be as simple as this, and it will never change. So when we have a shrinkage and an internal pressure, what is their relationship on a compound cylinder? On their compound cylinder, they're going to help us to find the actual values or the resultant stresses. So we're going to talk about actual or resultant stresses. These are going to help us on this issue. When we add values on the shrinkage and with the internal, they're always going to give us the resultant. What I'm saying is this: shrinkage plus internal pressure equals to resultant. That's what I'm trying to say. It means when they say calculate the actual or the resultant stress of maybe contact plate, it means you have to take the value that is here. If here it was 15, right, and you're gonna come and calculate the value that is here, and you get here as 10, right? It means the resultant stress is going to be 15 plus 10. Then it's gonna give you the resultant stress. Therefore, if I'm explaining like this, it means we always regard the two graphs to be added. Let's write two graphs like this. It's nice to work on graph, or especially on resultant, because it's easy to calculate. Then this is gonna be like this. This is gonna be like this. This is going up like this. This is going down like this. Then we know we plus it with what? We plus it with the internal one. Then the internal pressure, this is our P1. Then it's gonna go like this. Then equals to our resultant. One thing I will tell you about the shape of resultant, will always take a different shape. I'm not gonna guarantee and say that the resultant always stays like this, but the two, they always stays like this, depending on their values, how they will be apart from one another. But on this one, we're gonna come on the this is outer, right? This is in, this is out, this is in, right? This is out, this is out, this is in, right? So we always gonna look like this. We always gonna look at like this. We come here on the outer, we forget about the inner, we cancel the inner for now, meaning this in, we don't talk about in, we talk about out now. Means if I add this value here and this value here, it's gonna give me what? 0. 0 plus 0 is gonna be 0, né? We go up with our graph, then I stop here on this is D, right? This is DC, this is D, D, DC, D, D, DC, D, right? Then 0 plus 0 is 0. Then I go up with my graph. As much I go up here, I also go up this side. So this is my contact point between the two cylinders. Then I add this value here and I add it with this value here. So it's going to give me a value somewhere here, you see. Then our graph can go up here to this value. Then after here I go down with my graph, but I found out here it's 0. But this one here, it's a value. Do you see it? If here it's 20, then it's 20 plus 0. Then it means my graph will do what? Will go up. It means my 20 is going to be somewhere here. So then my graph will automatically go up with a parabolic shape like this. You saw that? And we are done with the a radial stress. Then let us look at the hoop stress movement. We come here, we're gonna get a negative number here. You agree with me? Even here we're gonna get a negative number. It means we're gonna have a negative number here. We come here, we're gonna get a negative number. Even here we're gonna get what? A negative number. It means this is gonna go like this. Do you see it? And we now do what? We come here on the inner. This was for out, right? Then we come here on the inner. We have a positive number. Can you see that? We have a positive number. This positive number is because of it's on top. Remember, this is positive. But we add it with what? We add it with a negative number that is here. So a positive plus negative. This negative will always be higher than this. So it means we're gonna take the sign of a higher number. Then we're gonna have a negative number somewhere here, right? Then now our hoop stress on the resultant will no longer be positive, according to this statement that sigma h and sigma r will both be compressive. So our on the resultant, our hoop stress will no longer be what? Positive, because of the value we add in here. So this value will always be bigger than this one. Then we'll take the sign of a bigger number. Then we're gonna have a negative number here. So we come here and where? And here. So here we're gonna have a bigger number. When I say bigger number, let me give you an example. Here we're gonna have negative 100, right? And here we have positive 25. I just want to give you a practical example, right? Then we have to add negative 100 and positive 25. Remember, it's compressive, it's positive, it's 100, it's tensile. So it's negative 100 plus 25. It's going to give us a negative 75. So when we come to draw our graph, it means it's going to have a negative 75 here. So you see, this is no longer a compressive. It's going to be what? A tensile, because of the sign of a bigger number. This is how we're going to draw our resultant force graph. I'm not really sure if in the exam they do ask about drawing the graphs, but in case it comes, let it be a breakfast for everyone. And this graph, why do we need to know them? They're going to help us to answer questions and to know where we can plot our values. I prefer graph method than any other method, but I still say it again, the alternative way is the one. The alternative method, they're always needed, but the one you know much better, keep on with it. The main thing is to pass. And I'm done with explaining shrinkage and internal pressure. I just want us to do an example and to know, like, what's this all things like actually, what is this guy talking about? The rest of other things I will show you along the way. the rest of other things. I'll show you along the way. I showed you the most important things. Let me look at the perfect example. We're gonna do from the book. Let's do number 2. We're gonna do number 2 from the book. Sit. We're gonna do number 2. Because I like it because it needs me to calculate the resultant there. That's why I'm choosing number 2. So that you can understand how to use this method of resultant. Okay, this is what I always do when I answer this kind of questions. I always do like this. I draw my stuff here, DC, big D, and small d. I know that this is gonna move like this, this is gonna move like this, this is gonna move like this, and I'm gonna have the top one going there. This is my sigma h, this is my sigma r, this is my radial stress, this is my hoop stress, like this. I plus it with the internal, and this is my internal. It's gonna move like this. This is my P1, and it's D, DC, D, and I move this, and this is my radial stress, this is my hoop stress. Then I say out, I say in, out, in. Then equals to, I don't really know the shape of my resultant, how it's going to stay, but it will be safe just to draw the estimated one like I showed you. This is gonna be like this, this is gonna be like this, this is gonna be like this, right? This is not this one is not gonna be available. This is going to be go like this. Yeah. So this is my just a simple structure of how when I'm answering questions. So we're gonna do 2.1. It says that when I do exercise 2.2 number 2, it says that the diameters of the compounded cylinder shell are as follow. Okay, they say they are as follow. I can just write on one. They said the inside diameter is 100. So my inside diameter is 100. The contact diameter is 150. My contact diameter is 150. The outside diameter is 200, and the outside diameter is 200. So and the statement continues. They say the normal pressure, they're giving us a pressure, a normal pressure at a contact surface after shrinkage is 20 MPa. Remember, this graph is for shrinkage, right? This is for internal pressure, this is for resultant, right, or actual stresses. So they say the contact place, the normal pressure at the contact surface after shrinkage is 20. So they give us a contact pressure. The contact pressure is here. So it means here they give me 20 MPa. They give me 20 here. So we continue, and they said an internal pressure is 60. Then they come here, they give me internal pressure, which is here. Then I know my internal pressure is 60. And on 2.1, they say calculate the maximum hoop stress for the outer cylinder. They need a maximum hoop stress. In fact, this question it might confuse you in a way. It was, according to me, it was not asked properly, because they just saying a maximum hoop stress for the outer cylinder. What I understand about the question and what they have allocated there, you see they put 127.01 MPa. During my calculations, I find out this is a resultant hoop stress. So they were actually looking for the maximum. Let me put the question right. They actually looking for the maximum hoop stress on the outer cylinder, right? But it's a resultant. They should have said calculate the maximum resultant hoop stress on the outer cylinder. That's what they were supposed to say. Maximum hoop stress on the outer cylinder. So that's what they have to say. It means if they need a maximum hoop stress on the outer cylinder, it means we look at the outer cylinder, right? We come here, we look at our outer cylinder. Where is our maximum? Maximum is always on the inside, so we know our maximum is here. And we come here. Here they say calculate what? Maximum hoop on the outer cylinder. Where is our maximum? So our maximum will be here. So basically we're gonna add this and this, then it's gonna give us a value here. You see it? It's gonna give us a value here. So the two will give us the value here. What they want is this here. So it means we have to calculate this package of shrinkage. We come to calculate the package of internal, then we add them together, then they're gonna give us what? Our resultant. Let us start on the shrinkage. So we're gonna come here and say shrinkage, right? We're starting on the shrinkage. First of all, what do we have? We have a contact, pressure. So I can say that pressure contact equals to A plus B. It's on a radial, right? Divide by DC squared. You see? Then I said 20 times 10 to the power 6 equals to A plus B divided by the diameter here is 0.15 squared. Then let me make A subject of the formula, and I will say A equals to 20 times 10 to the power 6 negative. I take my B, whatever, this side, and it's 1 into 0.15 squared, and which is 4 B. Then this is my equation 1. I'm on shrinkage. I got nothing to do with this. I don't even have to take any value going forward. I work here on this graph. I work on this one. So what else do I know? And remember, you're working on the outer, so it's best if you look on the information that is on the outer, right? But though it's the same graph, you can still pick anything. But now we have to look at this one. Here they told us that we know it's our QR is 0 at bigger diameter. Then it means our QR is what? A plus B into D, big D squared, equals to 0 at what? At outer diameter. At outer D, it's 0. Then we make A subject of the formula. A equals to negative B over 0.2 squared. Then A equals to 1 negative 0.2 squared is going to be negative 25 B. Then this is our equation number 2. Then we substitute A where? Here. Then A equals to 20 times 10 to the power 6 minus 4 multiplied by no, it's supposed not to be like this. It's 20 times 10 to the power 6. B equals to negative 25B. You see? Then I say 20 times 10 to the power 6 equals to negative 25 plus 44.44 close brackets B. Then B equals to, I add this and I divide it with this. Then it's 20 times 10 to the power 6 negative 25 plus 44.44. Then it's how much? It's my B is 1,03 times 10 to the power 6. Then I go to my A. When my A, I multiply it with 25. It's gonna be negative 25.72 times 10 to the power 6. Then this is my A and what? And B. It's my A and B. All right. Then from there, what do? I have to find the hoop here. I will name it hoop shrinkage, right? Then it's gonna be hoop on the shrinkage 1. Get 1. Let me name it 1. I'm sorry. Equals to A minus B. It's at the contact diameter DC then is equals to A, it's negative 2572 times 10 to the power 6 minus 1,03 times 10 to the power 6 divided by 0.15 squared. Then our answer is gonna be it's negative, sorry, answer it's negative 20 times 10 to the power 6. No, let me say negative 20 MPa. This is my hoop stress here. It means my hoop stress here is negative 20. Clear? Okay, I'm not done. It means I have to go and get what? I have to go and get my hoop stress here. Do you see it? I have to go and get my hoop stress here at this point. So when it means now I'm going to the internal pressure. I have to solve for internal pressure. Then it means for internal pressure, I already know this here it's what? It's 0. Then that's what I know. I know that A plus B divided by D squared is equals to what? 0. Then my A equals to negative 25B. Equation 1. I solve it here. You see, this thing is repeating itself. So it's negative that. Then I'm given PI. I know that my internal pressure equals to A plus B on the small diameter squared. And it's going to be 60 times 10 to the power 6 equals to A, which my A is here. Let me just substitute it right away. 25B plus 1 plus B into 0.1 squared. So 60 times 10 to the power 6 equals to negative 25B plus 1 into 0.1 squared, and it's gonna give us 100. So we have 100B. You see, then we add this, we're gonna have 75. Then is B equals to 60 times 10 to the power 6 divided by 75. Then our B equals to 60 times 10 to the power 6 and 75 is giving me 800 times 10 to the power 3. Then I multiply it with negative 25, multiply with negative 25 to get for A. Then it's giving me negative 20 times 10 to the power 6. Then I have to find this contact place here. It's my hoop, remember. Then I say my hoop 2 equals to A minus B into DC squared. Then I substitute my A, it's negative 20 times 10 to the power 6 minus 800 10 to the power 3 divided by 0.15 squared. Then I'm gonna get so I'm getting negative 55. I'm getting negative 55.55 MPa. All right, negative 55.55, negative 20. Okay. Something need to be rectified here. You see here we got negative 55.55 MPa. I think I punched my calculator wrong somewhere here. Let's come back here. I'm going to say negative 25.72 times 10 to the power 6 minus into 1,03 times 10 to the power 6, and we divide it by 0.15 squared. You see I got negative 20, and basically it's supposed to be negative 71, not 20, sorry, negative 71. It's important to verify your answers. MPa. And now it means we need the resultant, remember? So QR resultant equals to not resultant, not hoop, I'm sorry, Q hoop 1 plus sigma hoop 2, which is negative 55. No, the one is negative 71. And let's take out the 10. The 10 to the power 6 is 71.5 MPa plus negative 55.55. So plus 55.55, it's giving me negative 71.5 plus negative 55.55. It's giving me negative 127.05 MPa, which is the correct answer. You see, they got negative 12701. But I explained on the single cylinder that on a hoop stress, when you find the answer, you might get it without them putting a negative, but because they know it's a hoop, it has to be negative, and because it's tensile. All right, let's go to number 2.2. They say calculate the radial stress at the contact diameter. They say they need a radial stress at the contact diameter. If we come here and we look closely, we already have 20 on the contact, and we come here, we don't know the value that is here. So it means if we add this value here with the 20, we are able to get what is happening here. So it means it's simple. We already worked for internal pressure. You see here, we already here we worked for the internal pressure. So we just have to take value for A and B, then we find the QR here, then we're gonna get the answer. Let's do it here. It's sigma R, right, equals to A plus B at DC squared. You see, at the contact. So we need what? This. Then our A is what? We got it here. It's negative 20 times 10 to the power 6 plus B. We got it. It's our B. 800 times 10 to the power 3. Divide our DC at the contact. It's how much? DC at the contact is 0.15 squared. Then how much do we get? It's important to punch your calculator, right, to avoid mistakes and wrong answers. So I got 15.55 MPa. Then I have to add it now. It means I am gonna take this one, shrinkage. I'm gonna take the one at shrinkage. Let me say hoop radial stress at contact 1 plus radial stress at contact 2 equals to actual, the one they want. Then the first one is 20, which we are given, and the second one is 15.55. Then it's gonna give me what? 20 plus 15.55. It's giving me 35.55 MPa. So this is what they want. And coming here to look at the answer, we find out that the answer they got is 35.56 MPa. So it was a crucial question if you were not aware of it, because if you look at it, they said calculate the maximum hoop stress for the outer cylinder. So they actually did not mention if it's a resultant or on the shrinkage part, on the internal pressure. But one thing I will let you know is that if you check your information and your question, they never said on the shrinkage or on the internal. They just said calculated the maximum one. So it means they need the maximum from the resultant. So in your mind, just make it automatically. When it's for shrinkage, they will tell you straightforward that find it on the shrinkage. So such question, you know how it's gonna come. It's gonna come on the they're gonna break it down. They might make 4 or 5 questions from it. At first they say calculate this on a shrinkage on the internal, then the last question they're gonna say calculate the resultant. So they usually love to mix it like that. But rather than that, this is how you do your shrinkage and internal pressure and the resultant. I quickly want us to look at the last thing that I want to talk about. It's just a simple thing, to talk about. The equations. These equations, you're usually gonna find them, and the first equation that you're gonna get, it's a Paschen ratio. You need to know about this ratio. Actually, Paschen ratio, it speaks that the lateral strain divided by the longitudinal strain equals to Paschen ratio, which is dominated by a small v. So we're gonna say that v equals to E lateral strain and longitudinal strain. This is the equation for Paschen ratio. So go into your to the old question paper and see if there's nothing like this. And another equation that you must know, as much we were talking about shrinkage. When we are talking about shrinkage, there is going to be something called shrinkage allowance. Shrinkage allowance. It means it's more like if you know limits and fits. If you know limits and fits, in order to fit something, we have different types of fits, where we have transition, interference, and clearance. So all those fits, they're not going to fit the same. Some there's going to be easy to fit them, some they're going to be difficult to fit them. Sometimes you have to use dry ices, sometimes you have to use the nitrogen thing just to squeeze your cylinders. If they are metal, even if they are plastic, you can still squeeze them with the dry ices, and so you can have them fitted. But at the end of the day, there's going to be an allowance on how you fit. What allowance do they give? So check out this formula on your formula sheet. It say that delta D, which is delta shrinkage allowance, is diameter at the contact, your modulus, into hoop stress 1 minus hoop stress 2. So this is what it's going to happen. When they say hoop stress 1 and hoop stress 2, it means it's inner. 1 it's inner and 2 it's outer. So that is our equation for shrinkage allowance. What we have to note again, it's a torque transmission when we feed the torque transmission. When we look at the formula for torque transmission, we have to look at what is torque. We know that torque equals to what? Force multiplied by radius. We know this, right? And it means we need to know the force. On this one, when we feed, there must be a friction, of course. So this force, we're going to regard it as a frictional force, right? And when friction is concerned, we need to have a coefficient of a friction. So it means we're gonna look at the stress, which we're gonna name it as PO, which it's an intermediate pressure. It's intermediate pressure. Intermediate pressure. It comes from the intermediate pressure. Intermediate pressure. And you're gonna multiply it with an area. We can find a force without getting the area of the surface. You're gonna have the area multiplied by coefficient of friction. This is how we're going to get our force. So our area, because we're working with the most circumferential things, like it's going to be pi, diameter, and length. You see it? Pi, diameter, and length. This is where we're gonna get our area. And after we got our area, we're gonna use this to calculate F, then we're gonna substitute. So what about R, which is the radius? R is always gonna be the diameter you divided by 2, because we're looking for the torque transmission. It means we have to get the diameter on the contact. So this is DC, and you divide it by 2. So then our final torque transmission formula is gonna be FU multiplied by DC divided by 2. So this is our final formula, which you know this is what? Intermediate pressure, area, and coefficient of friction. So this is what we get from this formulas. I told you another thing that you must not forget. I'm just trying to recap things maybe I might have been missing out. When we are installing a solid, let's say this is a shaft, it's gonna be solid, of course, and this is the outer, the outer is Y, the shaft, it's the solid one is X. Always treat this as a single cylinder. Every time you're working on the issues like this, treat it as a single cylinder, which I showed you already what is happening with the single cylinder.